So the concepts of concavity and its related concept inflection points have to do with the second derivative of a function. So second derivative of a function is, of course, when you take the derivative of the derivative. You're taking the derivative twice, denoted as f double prime of x. So let's talk about what concavity and inflection points are first of all. So the concavity is a shape of the graph that basically means it's either opening up or opening down. So if you ever have a curve that looks like this, or a curve that looks like this, you can see on this curve it's increasing and then decreasing. This is decreasing and then increasing. That actually, the decreasing and increasing doesn't exactly have anything to do with the concavity. The concavity is which way is the graph opening. And in this case you would say it's opening downward. In this case, you would say it's opening upward. So this is concave down. This right here is concave up. So you can see if you put these two together, and you had something like this, like a cubic graph or maybe a trigonometric graph, there's some point here where it switches from being concave down to concave up. That point is called the inflection point. So let's talk about what these mean now in terms of the second derivative now that we've kind of defined them graphically. So, a function is concave up when the second derivative is positive. So this implies concave up. If the second derivative is negative, that implies that the function is concave down. Remember that concavity, this is a property of f of x. So if the second derivative of f is positive, then f is concave up. If the second derivative of f is negative, then f is concave down. So that might make you think, oh, well then the inflection point is when the second derivative is 0. And that's not entirely true. So, in order to find the inflection points are wherever the second derivative changes concavity. That's the important concept there, is that when it changes concavity. So what you want to do when you're trying to find inflection points of a graph is set up a number line using the second derivative's critical numbers. So all the numbers where the second derivative is either 0 or undefined. So let's say we have a couple second derivative critical numbers here, C1 and C2. And similar to how you check for relative extrema using the first derivative, for the second derivative you want to check numbers in each of these ranges to see whether or not that entire interval is positive or negative. So let's say we had this setup when you tried your numbers in this function. So you can see from negative infinity to C1, the function is concave down. From C1 to C2, the function is concave down. And from C2 on to infinity, the function is concave up. The question is, where would you have an inflection point? You only have an inflection point right there at C2. Even if C1, this first critical number of the second derivative, makes the second derivative 0. It's not that it has to be 0 to make it an inflection point, it's that it has to change concavity. So it's very possible that your second derivative could be 0 at a point and that not be an inflection point because it doesn't actually change concavity. So you have to make sure to draw your number line using your second derivative's critical numbers in order to find the inflection points of a function. But just the concepts of concavity and inflection points in general are all dealing with the second derivative, and sometimes using it graphically might be an easier approach too if you have the graph, but the inflection point, concave up and down, and using the number line are all really integral parts of these questions.